Alrighty, folks, so we are still in section 5-2. This is recording number 4. And primarily we're going to be talking about example 511. I think it kind of pulls together some really good concepts for us, so it's worth the time. Unfortunately, in this problem, or this example, there's a typographical error. And I'm sorry about that, but let me explain it to you. So here we go. 511 talks about a talk radio show. Talk radio station has four telephone lines. If the host is unable to talk, for example, during a commercial, or is talking to a person already, the other callers are placed on hold. Now, if you have more than 4 calls, that's more than 4 lines, anybody else, so the 5th caller, the 6th caller, and so forth, they're going to get a busy signal. So this is an example of a capacity type problem and a demand type problem. If the demand exceeds the capability or the capacity, bad things happen. The random variable up here, the x, that's 0, 1, 2, 3, 4, that is the number of callers. That's the number of callers. Unfortunately, the author makes a mistake here, and he says the probability that 0, 1, 2, 3, or 4 people will get through. Now, that's not exactly right. It's the number of callers is what we're talking about here. And my evidence for that is just right down here. It says the mean number of people calling at any one time is 1.59. So he got the mean here the normal way. So X is the number of callers. It's not the number of people. It's not the number of people that get through. You can have more callers than you have people that get through, obviously, okay? Now, maybe what he's trying to say here is that, yeah, it's a number of callers, okay, but they all get through because we have 4 lines. Maybe that's what he's trying to say there, but I claim it's not very clear. A better way of saying this is it's the number of people who are calling at any one time. In any event, we've got the random variables. 0 people are calling, 1 person's calling, 2 people are calling, and so forth, all the way up to 4. And we got these probabilities. If you add up these probabilities, they will add up to 1. So this is a legitimate probability distribution. So first thing we need to do, what's the problem? The problem is find the variance and standard deviation for this distribution. And then they ask a question. Well, should they get more phone lines, or is this going to be enough? Well, let's take a look. The mean is easy enough to calculate. We have a formula for that. The variance is certainly easy enough to calculate. A little bit tedious, but you can do it. Okay, and then finally we come up with the mu. We come up with the sigma squared, the standard deviation. I'm sorry, the sigma squared is the variance. Then the standard deviation is just the square root of the variance. We come up with these numbers. Okay, so we've got the numbers. That's what the author asks us to do. The more interesting question is, should they consider getting more phone lines installed? In other words, is the demand going to be greater than the capacity often enough to where they have a problem? Okay, now let's just think about it for a second. Suppose, for the sake of this discussion, that 80% of the time, 90% of the time, they had more calls than they had capability, right? That would be bad. Okay, that would be a bad thing. Okay, so what he's saying is, no, we do not have inadequate capacity here. We're okay. And why does he say that? He says the mean number of people calling, see, that's why I say that this really should be thought of as the number of people calling. The mean number of people calling at any one time is 1.59. There it is. Since the standard deviation is 1.123, most callers would be accommodated by having 4 phone lines. That's what they have now, because, now here's the crucial part, mu plus 2 sigma would be, here, mu is 1.59, 2 sigma is 2 times 1.123. That's equal to 3.836, which is approximately 4. So the capacity, one way of thinking about this capacity is, well, it's mu plus 2 sigma. That's 75% of the time is good enough. Very few callers would get a busy signal, since 75% or more of the callers would either get through or would be put on hold. In other words, the first guy that calls, maybe the host is talking, the second guy is talking to the producer, the third guy is talking to the executive assistant, the fourth guy is on hold, whatever the situation is. But they're being handled. The only way that they're not being handled is if they go to a busy signal. That's what we're trying to avoid here. Okay, so the crucial question here is, how in the heck does he come up with this? How does he know that at least 75% of the callers would either get through or would be put on hold? Well, that comes from Chebyshev's theorem in section 3.2. So let me bounce over to that right now. I'm gonna bounce over to that. I'm gonna stop recording for a sec. Okay, so here we are. This is on page 139 of that section, and this is talking about Chebyshev's theorem. So let's refresh our memories. What Chebyshev's theorem says is that if you know the mean and you know the standard deviation, you can come up with a very good rough guess as to where the data is going to be. Now, Chebyshev's theorem was discussed in chapter 3. So chapter 3 is talking about actual data. That's the frequency distribution business, okay? And I've made the distinction a couple times now. Chapter 3 is where you have actual data, actual measurements, and that's where we talk about Chebyshev's theorem. Chapter 5, we're talking about probabilities. Well, probability is just your best guess as to what the data is going to be. So Chebyshev's theorem applies to chapter 5 as well. So what Chebyshev's theorem tells us is what proportion of the values from a data set, either a data set that already exists or the data set that's going to exist in the future based on our probability distribution. Okay, and it's telling you, and here's the formula. So hopefully you're following along in your book. It's on page 139 of the new edition. Okay, so here it is. Let you read that. So the example they gave was, well, how about if k is equal to 2? What if we're within 2 standard deviations? See, that's what it says. The proportion of values from a data set that will fall within 2 standard deviations will be at least blah, blah, blah. So he used 2 as an example, and we come up with 75%. So if okay, so the example he was giving here, he had 2 variables. He had variable 1 and variable 2. So it has a mean of some number 70 and a standard deviation of this. At least 3/4, 75% of the data will fall between, the 70, that's the mean 70, plus or minus 2 times the sigma. Okay, so 70 plus or minus, well, 2 times 1.5 is 3. So it's 70 plus or minus the 2 sigma would be 73 and 67. So it's between 67 and 73. So here's how you get that 67 and 73. You add 2 standard deviations to the mean and you subtract 2 standard deviations from the mean. So that's what we mean when we say it will fall within is the key word here. It will fall within k standard deviations of the mean. Okay, so that's where that's coming from. So let's make sure you remember that or have it in your book. Let's go back to the section that we just came from. I'm going to put it on pause again. Okay, so we're back to the example. We're looking at the example 5-11, which is on page 269. 269. Okay, so what he's saying here is, okay, the mean is 1.59 callers plus 2 times that gives me 3.836 is approximately equal to 4. So the reason I said this was a little bit vague or maybe ambiguous here is what he should have said is because of Chebyshev's theorem, we know that there's going to be that 75% of the callers will be within 1.59 plus or minus 2 times 1.123. So whatever that happens to be, let me stop recording and I'll figure that out. Okay, so I got my little handy calculator out, and 2 sigma is 2 times 1.123. That's 2.246. So mu plus 2 sigma is indeed approximately 4.0. So 75% will be between mu plus 2 sigma. Okay. Now, what about what I just said? I said that to be precise, what Chebyshev's theorem says is it's plus or minus 2 sigma. Well, mu subtract 2.246 gives you a negative number. It comes out to negative 0.656. Well, how can that possibly make sense? How can you have a negative number of calls? It doesn't make any sense. So this is an illustration of how you can be so misled by just relying on formulas. And this is where I'm not trying to put down computer programmers, but software guys, computer programmers, they're notorious for this. When I was in the industry, guys would give us programs. We had to be very, very careful because they don't understand the mathematics. They just they just crank out the coding. The coding, C-O-D-I-N-G, the computer code. What the author didn't mention was, okay, it's plus or minus the 2 sigma, but the minus 2 sigma doesn't make any sense, okay? So I guess maybe I'm belaboring this point, but you're going to get at least 75% of the calls between 0 and 4 calls, okay? Because if you're at negative 0.656, if you're at a negative number, that just doesn't make any sense for this physical problem that we're in, okay? All right, so that's where that comes from. So what he's saying here is that Chebyshev's theorem tells us that 4 is good enough. 75% of the calls will be less than 4 calls, okay? Well, what about those other 25%? Well, the heck with them. We're not going to spend all this money to increase our capacity just for 25% of the calls. So that's kind of the analysis here that you would do if you were trying to do this. Now, nobody cares about telephone calls to a radio station, but you can see how this would be a very important issue if you were trying to figure out, well, what kind of capacity do I want for my, for sending my emails, for sending my text messages, for sending my Instagrams or what have you. Believe me, there's guys that figure this stuff out all the time. And maybe for them, they would say, whoa, 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 25% don't get through? That is unacceptable. All right, so I hope I've explained this to you. I hope you understand what's going on here. It's putting it all together for this problem. It's a good problem. I urge you to spend the time on it because it definitely points out a couple of things that we need to know. It's talking about how to figure these things out, how to figure out the mean, how to figure out the standard deviation, and so forth. It also gets us into a review of Chebyshev's theorem, and that's valuable as well. So this is the end of this recording.